Hello, for Data Communications and Network 1 class today, I am Usada Tanjulaves. I will talk about data transmission, okay? Now, what is the definition of data transmission? Let's look at the definition of data first. Data are anything, any entities, okay? Anything that has meaning inside. So if you send something and it doesn't have meaning, it is not considered considered data. Signals. When you transmit something, you will always hear about signals, signalings. Okay, what are these? These are the representation of data. Okay, in terms of electric signals or electromagnetic signals. Okay, that can actually propagate or travel. Okay, along the medium. And what are the medium? The medium can be air, can be wire medium like twisted pair. Okay, which is copper wire that we use in telephone network. Okay, it can be fiber optics. Okay, like this. These are the medium. Okay, for transmission. So the signal has to be actually physically travel along the medium. Okay, so that it can, represent the data and go to the other, to the other side, to the destination. Now, what is the transmission? Transmission is communication of data by, okay, have to include propagation. Okay, propagation is traveling through the medium and processing of signals. Okay, so it have to be able to interpret, to detect the signal, to understand what it means. Okay, so the transmission include also the processing of data. Now we look at the spectrum of speech and music. Okay, this is the frequency domain, okay, or the component in the frequency component of a signal. Okay, if you have heard of the Fourier transform, you know about this, right? Fourier transform convert the time domain signal into frequency domain signal. If you have not heard about it, think about the tone in the voice or in the music. Okay, so the tone, high tone, low tone, those are the frequency component of the speech and music. Speech is something people talk about, like that what we voice that we are talking about. The music is like music instrument. Okay, and this is the spectrum. Look at the speech. Okay, the speech is about from 100 hertz to about 8 or 9 kilohertz. Okay, so depend on people. Different people has like different tone of voice. For telephone channel, okay, we allow only from about 400 hertz to about 4 kilohertz. Okay, 3 or 400 hertz to about 4 kilohertz. So if you talk to your friends, okay, over the phone, sometimes their voice are different from when you are talking face to face, because some of these that voice spectrum are not transferred through the telephone channel. Okay, and this is music. Okay, so music start from here to here, about 20 kilohertz. Okay, so music instrument give you like wider range of the bandwidth. Okay, now AM is only up to here, FM is up to here. Okay, so if you send music, song, okay, through telephone channel, a lot of it will be cut off. This one will be cut off. If you send it through the AM radio, then less of it will be cut off, but it will sound best with FM, right? Because it allows the wider range of the bandwidth, okay, for the music, okay, for the signal, okay. And this axis is the frequency domain, or frequency in hertz axis. Okay, now what is the channel capacity? If you think about this easily, you can look at it as a pipe, okay, that transfer water. Okay, so if you have two pipes, one of them has smaller diameter, okay, capacity is low. One of them has higher, wider diameter, then capacity is high. Okay, so you can send a lot of water, okay, at the same time. So it's like the water rate, okay, is higher than when the diameter is smaller. Okay, so if this is the channel, communication channel, if you have higher channel capacity, you can send more data or higher data rate. Okay, so in the real definition, so it's the rate or data rate, okay, that can be transmitted over a given channel part or channel or communication part or communication channel, which is like, think of it as a pipe, okay, under given condition. Okay, so with specific conditions that are given right now, what is the channel capacity that you can do? Okay, what is the base channel capacity that you can do? The key conditions for channel capacity are the bandwidth and the noise. Okay, sometimes we look at it as for the noise, we look at it as the signal to noise ratio. Okay, sometimes it's given as SNR or S over N. Okay, because the signal power you can fix. Okay, so it depends only on the noise. So sometimes we say it depends on the noise. Sometimes we say it depends on signal to noise ratio. Similar thing. Okay. Now signal to noise ratio in dB is 10 log base 10 of signal power over noise power. So signal to noise ratio in dB. Suppose I have this is signal power is 10 watt, noise is 1 watt. Okay. So I have this one is 10, right? Log base 10 of 10 is 1 multiplied by 10, so it's 10 dB. Okay, so this is the signal to noise ratio in dB. If this is 100, it's going to be 20 dB. Channel that prove that the maximum channel capacity is this formula. This is a very important formula, okay, that we will use. Okay, it depends on the bandwidth B, okay, and the signal to noise ratio. Be careful that this is in ratio. That's why I wrote it as S over N. Okay, it's in ratio. It's not dB. So if you have 10 dB, you have to convert it into ratio. So this is the same, okay, 10. But if it's 20 dB, you convert it, it's gonna be, the ratio will be 100, okay? So you have to put 100 here instead of 20 dB. Now let's look at the condition for this formula to work, okay? It's work in the AWGN channel, okay, which is additive wide Gaussian noise channel. Gaussian noise channel. Okay, this is the basic channel where we study in undergrad school, okay, for engineering, because this is the noise that is always there. Okay, it's an additive noise. Okay, so it adds to the signal power. It's white because its power spectral density is constant. Okay, power spectral density is the frequency domain. Okay, of the noise is constant. Gaussian because the power probability distribution function is Gaussian. This is in terms of statistics. Okay, we may talk about this more in a little bit in other clip. Okay, but right now this formula works in the basic channel. Okay, for other channel it will be more complicated. Now let's look at the channel capacity for the case that you have infinite bandwidth, because you see you have the B in front, okay, C equal to B log base 2 of 1 plus S over N. So you may think that you increase bandwidth to infinity. This one, channel capacity may increase to infinity too, but that is not true, okay. I will show you. To calculate this, we will use some relationship here, mathematics relationship, okay. For very small x, okay, these three are true, but the one that we will use is the second one. Okay, you can try. Okay, put in the your calculator small x, okay, 0.0 something, okay, and put in and see whether it's going to be approximately like this or not. Okay, we'll use a second formula here. From the capacity equal to B log base 2 of 1 over 1 plus S over N, okay, I can separate, okay, N equal to noise power. Okay, this is actually equal to N naught O times B, where N naught is the noise spectral density. Noise spectral density in frequency domain, okay, multiplied by the bandwidth. Okay, so actually I have bandwidth inside, other than the outside multiplied directly, I also have bandwidth inside. Now, if bandwidth go to infinity, this is, I define this as x, okay, x will be very, very small, right? So if I use this formula here, relationship here, I will have, I can take the log out, right? Log base 2 out and get x, okay, outside here, x log base 2 of e, right? But because I have b times x is this, okay, log base 2 of e. Okay, so I can cancel b and b, right? And that's why I got this, and this is the relationship that I get, okay? When b go to infinity, channel capacity will go to a constant, not infinity, okay? A constant, there is an upper bound, okay? If you look at the graph, you can see that the blue line here is the bandwidth go to infinity. C will be S over N naught log base 2 of E, which is a constant. This is the blue line. Usually, if the bandwidth is not going to infinity, it's going to be this line, okay, that go up like that, okay? So this is, so bandwidth go, this is the bandwidth, right? Bandwidth go to infinity. You will not get C go to infinity, okay? Now let's look again. If you have the signal, okay, power, you increase the signal power, okay, capacity will increase, right? But signal power, you see that is inside the log base 2. So if you increase the signal power, the capacity will not go up linearly either, okay? It will go up lower than the signal power that you put in, okay? But the bandwidth, okay, which is outside, you have to be careful that it's also inside the formula. Okay, so that's basically what I want to tell you. Now, we will recall, okay, the gain and attenuation in dB. I think everyone know about this already. So just recall that if you have a system, okay, and you have power in watt, okay, power in and power out, P1 and P2. Attenuation means that output is less than the input, right? So if attenuation is a positive number, it means that output is less than the input. So attenuation in dB, the formula will be 10 log base 10 of P1 over P2. So input is higher than the output, that's why it's positive number. Now, power is V square R, right? The voltage, V square R. So if it's become the voltage, this one gonna be 20 log, because the have V square, right? And the square go down to this, it become 20 log. Gain will be opposite in sign, okay, to the attenuation, because gain is defined as the output over input. Because if it's a gain, it means that it's increased, the power is increased, okay? So output power, P2, must be higher than the input power. That's why you have a positive gain, okay? Now, if you have attenuation, okay, of plus 3 dB, you will have a gain minus 3 dB, okay, and vice versa. If gain is plus 3 dB, attenuation will be minus 3 dB, okay? And this is the definition of the input power and output power. And this is the reference, okay? Thank you very much.